Dr. Andrew Sims and Lorenz Eberl are both in the simulation team at ResMed, both senior engineers. I think Andrew leads the team, and they've been using both ANSYS CFD and ANSYS FEA for many years. So they've got lots of things that they could show you. Some of them they're not allowed to, but very interested to see what they've got here today. ResMed is also a Creo customer, and I think there's a lot of other people from ResMed here today as well. So thank you, Andrew and Lorenz.
While Lorenz is getting set up, so I'm Andrew, that's Lorenz, and if you want to click it, thanks. There. Lorenz will start.
Thanks, Nick, for the introduction. So I'm Lorenz and this is Andrew. We both work at ResMed. Like Nick mentioned, we use sort of Creo and ANSYS extensively every day. So a little bit about ResMed. We have sort of 6,000 employees globally. 1,500 are right here in Sydney. And ResMed's probably best known for treating people that have sleep disorder breathing or sleep apnea. At ResMed, we're probably about using ANSYS for sort of 15 years, both in CFD and FEA. We have about sort of 10 full-time users of ANSYS and probably about 30 to 40 part-time. So as I mentioned, we probably deal mostly with sleep apnea or sleep disorder breathing. So what exactly is sleep apnea? So most people, when they sleep at night, their airway stays open and they can breathe perfectly normal. If you have obstructive sleep apnea, your airway actually physically closes while you're sleeping. You actually physically stop breathing. Your body eventually convulses and you start breathing again. But for people that have this, it's about 1 in 10. You actually get a bit less oxygen. You wake up feeling very tired and fatigued. All sorts of other chronic health-related illnesses which follow from that. It's also very disruptive to your partner as well because you're not sleeping well at night. Click forward. So the gold standard for the treatment of sleep apnea is to use one of these sort of devices. This is a sleep apnea machine, and it provides sort of slightly pressurized air that keeps your airway open while you're sleeping. This is a close-up of our flow generator. It has a humidifier tub beside it, so I'm going to talk a little bit more about this tub. The tub is sort of filled with water. It just opens. It's got a heater plate underneath. So air comes in from the flow generator, passes back out, it's heated and humidified, and then that goes to the patient. Makes for a more comfortable night's sleep, so you can sleep well with your partner and wake up feeling refreshed. So as I mentioned, I'm going to talk a little bit more about this tub and some of the simulations we use for it. So the tub is sort of heater plate underneath, flips open and closed. And before we go and spend probably tens of millions of dollars on making like a fully automated injection molding tool for this, there's a couple of checks that we want to do to make sure this actually works. And one of the sort of more critical cases is actually a misuse case. So imagine you fill this thing full of water, you then put it into your very expensive flow generator, and you sort of walk with that to your bedroom. We want to make sure that none of the water leaks out and goes into any of the electronics or motor inside here. Also want to make sure that if you tip it, or it falls off your bed while you're sleeping at night, water doesn't run down the tube and actually drown the patient. That's probably a little bit more serious. So before we can go spend a lot of money on that, we do some simulations to check that it actually works. So from Creo, we sort of use that, we bring that into Space Claim, we get our air volume. So the bottom part of the tub is sort of water, and the top part's air. And we spend a lot of time trying to design these sort of special inlet and outlet tubes to try and minimize the water flow, water loss coming out of it. So we then take that, bring that into Fluent, we do some meshing. So this simulation used a cut cell mesh, 800,000 elements. We then send it off to get solved, so we wait about 14 hours on 32 cores, produce 90 gigs of data, and we get this. Simulation where we just flip the tub upside down. We can see we get a bit of water sort of pouring out the inlet of the outlet. I just flip it back around for the sake of it. Couldn't actually show you an actual tub because we've got a lot of IP problems with showing that sort of thing. But we can then go through a lot of design iterations to try and minimize the amount of water loss that we have. We can also then do things like graph this result. Like all engineers quite like a good graph. We can sort of see trends where we're getting a lot more water loss in some areas than other. And we can go through design iterations to minimize the amount of water loss that we have. I'll now hand over to Andrew to talk about a couple of other examples that we have.
Thanks, Lorenz. So I'll take a little bit of a shift and we'll move on to a little bit of structural work and something I've spent a lot of time on, which is elastomers. And they're great things, and we use an awful lot of them. But I don't know if many of you are familiar with elastomers at all, but they're particularly fun things to deal with, and they have a lot of quirks. So they have some pretty complex material properties. Brought one. This is one they actually used for this particular project. But they're very stretchy. They eventually lock up, so they're highly nonlinear. One of their quirks, and one of the reasons it makes them fun to model, is also they're essentially incompressible. So that makes for some mathematical conveniences, but it also means the whole linear theory falls over and we have to use hyperelasticity or some other methods to solve them. So hyperelastic models, they essentially relate stress and strain via a different type of constitutive model, which relates the strain energy density function to a measure of strain, and that the derivative of let's start again. The stress is related to the strain through the strain energy density function by taking the derivative with respect to the strain. And the function W, there are a vast array of energy density functions. In this case, I've just shown about the simplest one you can have, the Neo-Hookean. It's actually one of my favorites. It's simple. For a lot of things you do, it can be made to give some really good results, and it's really robust. A lot of other models with higher number of parameters, they can lead to a lot of erroneous or even completely garbage and dangerous results if you don't do multiple modes of testing. So, as I mentioned, best practice normally for an elastomer is you need to test in multiple independent modes of deformation and then fit those simultaneously to a model to match your curves. But you actually need a lot of specialist equipment, and it takes a long time to do this. You may not be able to have the time, the equipment, everything else, which is what happened in this case. So in this case, taking advantage of a simple model and then using some inverse analysis techniques, we could use one of our previous products. So I think Lorenz had here this is one of our current pillows masks. So instead of a full face mask, which actually we've got here, this is one that seals on the inside of the nostrils and maintains pressure there. So this is one of our earlier version ones, but it just happens the material is exactly the one we're using on a current project. And we needed to deal with basically getting a newly molded material out of a tool and further into a production process. So didn't have time to do the full suite of testing. So essentially mimicked a test on this and then fitted the really simple model to it, and were able to progress really well. So just cut the headgear into bits, a bit that was basically close enough to straight, but it wasn't good enough to say that it was a uniaxial test specimen. So the actual profile blends and changes, and we've got all sorts of subtle changes on this, which meant we couldn't just go, oh, here's the area, force on area is stress, wouldn't work. So we mimicked the geometry and the test in the FEA model. Actually, I'll just divert a little bit. This is the actual test results that we got from this specimen. There's a lot going on. So the test was a cyclic load, so we pulled it a little bit, then a bit more, and then a bit more again, and you can see how highly nonlinear it is. There are a number of, I love this chart actually. It shows a lot of the quirks of elastomers. One, you can see that the hysteresis, it's obvious. The rising curves are different to the falling curves. So it's important to know how you're loading your material. Is it rising, falling, or is it cyclic and doing both? And you need to take both into account. Another thing which is really interesting is that they're strain history dependent. If you look at one of those loops, you'll see that the first time you pull it, it follows a markedly different curve to the second and subsequent times. But also if you look at the second and subsequent times at each level, they progressively get a bit softer and the peak drops down, but it eventually stabilizes. So that's called preconditioning. It's also an example of that incorporated damage is often grouped together under the term the Mullins effect. And it also results in essentially a not entirely permanent, but a an offset of the origin a little bit and some long-term set back at the resting configuration. And finally, we also see strain level dependence. So the rising and falling curves are markedly different depending on the strain level that you go to. So it's not just a matter of pulling this, getting a number. You have to really understand what you're doing, how you're testing it, how you're loading it, and then use the appropriate data. And then all that's with the understanding that, for example, hyperelastic material models, well, they are what they say. Hyper, very large, and elastic, they don't take into account inherently in themselves any energy loss or hysteresis. So you have to choose and tune your model appropriately if you really want to get high fidelity results. So for this particular model, we were interested in fresh material coming off a tool and in really high strain levels. So one of the neat things about this test, though, is that you might notice from the first cycle at each strain level, the elastomer, when it goes into sort of a new strain history, or it propagates into a new strain history, that the curves continue from where the previous cycle left off. So let's see, does this pointer work? So we can see here it's sort of stabilized around here, and then the next time we come up, we follow up under here and then follow that new curve. And you can see similarly, after it's stabilized here, follow that curve up the top. So the advantage of that means we can just do one test, get really rich data sets, and then, but in this case we're interested in the first cycle data, so we can build a composite load curve on the left, taken from the first cycle at every load level. And the other convenient thing in this case is that that curve shape approximately matches the type of curve shape you can get from a neo-Hookean model. So all the things are aligning into what we want to do. So we built our FEA model. That was quite the easy bit. So just essentially took our CAD model and meshed it. In this case, that was meshed in ISOM to just get a really quick hex mesh on it. And then because it's an elastomer, we had the usual things of having to use large deformations, the hyperelastic material, you can't do one without the other, and you need to enforce a mixed displacement pressure element formulation. So if any of you don't know that, it's the key option MAT ID 6.1. So key option 6, set it to 1, gives you the mixed UP formulation, and that's needed to cope with the incompressibility. And in this case, we did a two-stage solution. So the first one pulled just a little bit and then updated the geometry and mesh, reset the strains, and then did the primary stretch. And that accounted for the little offset at the beginning. And then we just allowed this solution, any hyperelastic material, you have to do a curve fit to extract your material properties. In this case, the fit was done to the actual experiment, not the stress strain data, and we essentially just brought that into the optimization loop. And this can be done any number of ways. So it can be done with an external optimizer, MATLAB, Python, and I think we spoke to, what's the package? OptiSlang. It can be done in that too. And you can also make Design Explorer do it as well and keep it all within the ANSYS Workbench environment. So, on to the results. It's not that impressive just pulling the thing straight, but you can see how much that we stretched it. But just after a few iterations, we're able to get a really good estimate and curve fit to that experimental result, and that allowed us to progress and do some much more complicated modelling with a calibrated material data set, which allowed us to then guide some design decisions which were related to tooling. So as Lorenz mentioned, this had an impact of potentially millions of dollars on our production cycles, and it also able to inform some future manufacturing process conditions and how we programmed our robots and other things. So it was a simple project, but a really neat little one and interesting one. So now, instead of a little bit of a deep dive, just like to show a few other snippets of some types of things that we've done. So in this case, it's another manufacturing based solution, but it's one on a fluids design. So in this case, the problem here was really getting this model to run. So we've got very large difference in dimension scales to deal with here. We've got down at sub-millimeter levels for some of the flow details and geometry details that we needed to get for this jet of plasma to impinge on around this mask. And then part of this tool is a mask similar to this. So we're dealing with a dimension scale there of probably 100, 150 millimeters if you look at the flow path that we needed to take. And then we needed to have this thing moving, and so time and dimensions conspired against us. So if you were to just have a static mesh there for that, it would have been unsolvable. So we ended up using an oversetting mesh technique. So we had a complete 2 overlapping volumes with an interface region combined in fluent, and then one was allowed to move across the other. The three-dimensional path was taken from our robotic path, and then we defined a user-defined function which basically mapped along with the tool head a refinement region, and then used adaptive meshing to both coarsen and refine. So we had a moving refined mesh region follow along with that head, and the result of that was we're able to get something which could solve within a day or so and provide us with a good information to again make decisions about on our manufacturing process. And finally, another cool thing, we have to remember that we deal with people, and we've spoken a lot about machines here today, but it's the patient and the people, and people are really at the front line of where our products work, and we have to remember that. And the face is a complex shape, and we're dealing with people when they're at some of the most vulnerable times, trying to sleep, and it's relaxed. And that's not really the most relaxed thing that you can bring to yourself. So we need to do a lot of work to make our masks comfortable. And a lot of that comes down to the shape and the fit. And if we don't fit well, they can leak, they can leave red marks and so on. So it's a big effort goes into making really comfortable masks. And one of the tools that we can use for this is some finite element analysis to look at the interface between the mask and the face. Over the years, we've done a lot of work on this area as well, and it's a really complicated one to model. There are extremely large deformations and complex shapes, and we're also dealing in an unstable regime where we've got post-buckling deformations happening all over the place. So just in this case, just to show you how we've done there, you can see a number of the complicated post-buckling deformations here, and explicit analysis really helps us out in this case and makes this kind of work possible for us. And with that, I'd like to just say thank you for letting us give you a quick rundown on some of the kinds of work that we do at ResMed and the tools that we use from LEAP and ANSYS there over, it's well over, I've been there for more than 12 years, and ANSYS was there before I came. And thank you for your time, and we'll be around all day, so if you want to chat to us, feel free.